Hello students, welcome to Inside Physics. Today we will discuss the applications of Gauss law. Gauss law we all know it related to electrostatics and it tells something about the field, electric flux, the relation between electric flux and the electric field. So according to Gauss law, which we have discussed in our previous videos, the total electric flux coming out of any closed surface is equal to 1 by epsilon naught times the total charge enclosed inside the area, inside the surface. That means flux is always represented by phi, and here we will say that according to Gauss law we can write flux as q by epsilon naught. That means 1 by epsilon naught times the total charge enclosed inside the surface. So here we understand to apply the Gauss law to any surface, we need to take the surface and around the charge. So we will calculate the electric flux. And what is the relation between the electric field and electric flux? According to the definition of flux, what we have seen previously, we know that phi is equal to E bar dot ds bar. This is a small area, so we can take the flux as a small flux. That means this is as simple as that. If you take an area perpendicular to this board like this, so the electric field passing through this surface, so this is the electric field, electric lines of force passing through this area which is considered as perpendicular to this board, and the lines are passing through this area. The total surface area is S. If you take the small area in this surface, this is ds. Total surface is S and this is ds. So total flux passing through the surface S is phi, and the small flux passing through this small surface is d phi. So here, applying these two principles, Gauss law and the definition of electric flux, we will calculate the electric field of some of the conductors of different shapes. Those are called applications of Gauss law. In these applications, there are three we take. The first one, infinitely long current carrying conductor. So we will calculate the electric field applying Gauss law to the infinitely long current carrying conductor. For that we will take an infinite long wire which is having a positive charge around it, on it. So the surface of the electrical wire is having a positive charge, so the length is infinite. How to get the electric field due to this conductor? So for this, to applying Gauss law, we need to imagine a surface around this conductor. So the appropriate surface covering the area around this conductor must be a cylinder. So whatever the area we take, it must exactly represent the electric field, and the surfaces that we take as a structure, the electric field must pass through the surfaces. So here we will take an imaginary cylinder around this conductor, which is having a radius small r, and length of the cylinder is L. So why we have imagined this cylinder means, according to Gauss law, first we will calculate the flux passing through this given surface. The charge enclosed inside the surface is the cause of electrical flux. We all know that this field coming out of this because of this charge is radially outwards along the radius. We already discussed about the electrical field. So if you take a point P here at a distance r, which is radius of the cylinder, the electric field at all points on this surface is equal, because the points, all the points, if you take a point P here, so if you take a point P dash here, if you take a point P double dash, all the points will have the same electric field, and the electric field here, if you observe, only depends on the distance from this axis. We can say this is axis of rotation. If you can rotate the cylinder, it has a symmetry of rotation, and all the points on this surface will be equidistant from this axis. So here, how to get the mathematical relation to get the electric flux? We know that E bar dot S bar is equal to, and Q by epsilon naught. This is what we know. Here the cylinder will have a surface charge. See, this conductor will have a linear charge density of lambda. So initially we need to assume that the conductor is having a linear charge density, means the charge present on the wire per unit length is called linear charge density. This is represented by Q by L. So the length of the wire, what is the length of the wire? We have taken L, nothing but the length of the cylinder also. So here the surface area, how to get the surface area, means you cannot take the surface of the total cylinder. You need to take the surfaces through which the electric flux is coming. If you observe here, the electric flux is coming through this surface only, this cylindrical surfaces only. The electrical flux will not come through these surfaces. This is a surface. These surfaces is not having any electrical field coming through it. Only this is the surface through which all the electrical flux will be. Flux is nothing but field lines only. So that is the surface we need to take. What is the surface area here? This is the perimeter. If you observe this circle, this is the perimeter. That means 2 pi r is the perimeter of this circle. This is multiplied by the length of the cylinder, gives the surface area, not these two surfaces, only this surface area of the cylinder will be given as 2 pi rl. So here if you take electric field into 2 pi rl, Q is nothing but lambda L from this by epsilon naught. So L will be getting cancelled. So electric field, here we have not taken any vector in the vector form. Okay, 2 pi r L gets cancelled, so we can directly write the electric field is equal to lambda by 2 pi r or 2 pi epsilon naught r. Okay, so if you want to take it into the vector form, you can put a bar here, and this can be multiplied by the unit vector which is in the direction of radius vector, that is r cap. The r cap is a unit vector which gives the direction radially outwards from the axis. Okay, so this is how we calculate the electric field due to a infinite long current carrying wire, charged wire. So next, second one, an infinite long plane sheet, electric field due to a infinite long plane sheet. So the same theory will be applied for this plane sheet. So the sheet will be, if you consider a plane sheet which is infinite measurements. Okay, this is a this is assumed to be a plane sheet. So what we need to do, the area is, if the plane sheet is infinite measurements, the area is also infinite. For this we need to take a small area only, right? We need to take a small area in the sheet. The area may be considered as like this, or you can take a little bit bigger area. So this, see, you need to imagine this sheet, infinitely plane sheet, like this, perpendicular to this board. Then only you can easily understand how we are taking the concept by imagining a rectangular box like surface around this considered area. So if this is the area of the plane sheet, this area, and we will imagine, see, we will take a rectangular box around the area. How will we take the rectangular box here? See, so this rectangular box must be imagined. See, if this is the plane sheet, see, this is the area of concern. There must be a rectangular box this side and this side. You imagine this plane sheet like this. So if you can observe this rectangular box, the flux coming through only two sides only, right? The flux will be coming through two sides. This is one side which is having a surface area S1. If you consider this surface area as A, and this is also the surface area A. So both having same surface, the flux because of this plane sheet will be coming through these surfaces only. Okay, and the flux will not come through these surfaces. There is no flux in this direction, because the plane sheet is like this and we are imagining a rectangular box, so the flux will be in these two surfaces. So now, according to Gauss law, the total electric flux coming out of the surface area is equivalent to 1 by epsilon naught times the charge enclosed inside this rectangular box. Here the surface area we have taken is the rectangular box. So for that, what we need to understand, the flux coming through this area is EA, right? And the flux coming through this is also EA, because both areas are same. This area and this area are same. So the total electric flux means EA plus EA is 2EA. Okay, and the plane sheet having a surface charge density, that means represented by sigma, that is nothing but Q by A. The plane sheet is having a surface charge density sigma, which is given by Q by A. So here we all know this 2E total electric flux is equal to Q by epsilon naught. From Gauss law. We have taken this from Gauss law. Okay. So what is Q here? 2EA is equal to sigma A. From this, Q is equal to sigma A by epsilon naught, and here A is cancelled. That means electric field due to an infinite plane sheet is equal to sigma by 2 epsilon naught. So this is the electric field. So if you take it in the vector form, this will be E bar is equal to n cap. What is the direction of this unit vector n cap? Along this direction, from this direction. Okay. So this is how we calculate the electric field. This is the second application, and the third one we will go through is thin spherical shell. That is the third application. So what we are doing here, we are calculating the electric field of different conductors, charged bodies. So here we will take a spherical shell of radius capital R. This is the origin. So this spherical shell is charged spherical shell. So what we need to do, we need to imagine another sphere which is very apt to calculate the electric field using Gauss law. We will imagine another sphere. Here there will be two cases: electric field outside the sphere and inside the sphere. We need to calculate both. If you take a sphere, imaginary sphere around this sphere with radius r, small r, and the sphere is having a radius of capital R. So the surface area, see here, the surface area of this sphere, the outer sphere which we have imagined, is nothing but, what is the area of the sphere? We know the formula. Area of the sphere is nothing but 4 pi r square, where r is the radius of the sphere. So here we know again the formula will be Es is equal to Q by epsilon naught. So the sphere, inside sphere, is having a surface charge density again sigma, which is nothing but Q by epsilon naught. So here electric field into the outer sphere, imaginary sphere, this one is having a radius small r. That means the surface area, S means surface area, is equal to Q. Q is nothing but again, okay, sigma surface charge density. Actually this is nothing but Q by S, surface charge density. So here Q is equal to sigma S by epsilon naught. So what is this surface area? The left side surface area is the Gaussian surface area. Any surface imagined to calculate the electric field around this charged bodies is called a Gaussian surface. So the surface area here is the surface area of the Gaussian surface, and here this is the surface area of the charged body, that means inner sphere. So what is the surface area here? 4 pi r square is equal to sigma S means 4 pi capital R square. This is the surface area of this charged sphere by epsilon naught. If you observe here, see this 4 pi will be getting cancelled. So what is the electric field? electric field is equal to this sigma r square. I will write here on the top. So E is equal to sigma r square by epsilon naught r square. From this I have written here. Okay. So what is sigma? Again Q by S, right? So from this what we can write? Electric field is equal to sigma means Q by S. So Q by S into R square epsilon naught R square. So what is S? Again 4 pi R square. S is the surface area of the charged body. So here finally we will get the electric field due to a charged sphere at a point outside the sphere. If it is a point P at outside the sphere having a radius of small r, this can be considered as 1 by 4 pi epsilon naught. This S is written as 4 pi epsilon naught and see 1 by 4 pi epsilon naught, and r square will be getting cancelled because 4 is S is equal to 4 pi r square. So r square will be getting cancelled and this is nothing but Q by r square. See here, if you put in place of S, if you put 4 pi r square, 4 pi, this r square will be getting cancelled and this is comes to be like this. This is, if you observe this one, you remember one thing. This is nothing but the electric field due to a point charge at a point P which is at a distance r. Right or wrong? So from this is electric field due to a point charge. The sphere is considered to be a point charge and the point is the point charge is located at a point at the origin of the sphere. So an electrically charged sphere can be considered as a point charge because we got the formula for a point charge. So next, this is for outside point. What about inside point? If you consider again this, see, we will redraw the diagram again. What is about the inside point? A point which is inside the charged sphere. This may not be as good as a circle, but see, the radius of the sphere is smaller and I will take a small point here which is at a distance smaller, and this is the Gaussian surface. See, we are calculating the electric field due to this charged sphere. This is the case B. Case A is a point outside the sphere. Case B is a point inside the sphere. So this is the Gaussian surface. So is there any charge enclosed inside the Gaussian surface? That means the sphere imagined inside the charged sphere. So here there is no charge because all the charge is outside the imaginary Gaussian surface. So according to Gauss law, if there is no charge enclosed inside the surface, the flux will be zero according to this formula, where Q is the total charge enclosed inside the Gaussian surface. So here there is no charge inside, all the charge is outside this sphere. So we can take the electric field inside the surface, inside the charged sphere is equal to 0. Okay. So this is the third application. Yeah, using this Gauss law, something like these kind of applications, we can apply the Gauss law to any kind of surface. Okay, we will see some interesting topics in electrostatics in the next video.